Hello everyone. In this video, we will study the draft tube and draft tube theory. Okay, what is mean by draft tube? In previous videos, we have covered the all the types of turbines and the the design procedure for it, the reaction turbines and impulse type of turbine. So in this video, we will study draft tube. The draft tube phenomenon we have learned while studying the Kaplan turbines and all. So draft tube, generally the definition of draft tube we have familiar with it. Uh, Again, I am repeating, the draft tube is nothing but a pipe of gradually increasing area. Okay, pipe of gradually increasing area which connects the outlet of runner to the tail race. Okay, pipe of a gradually increasing area which connects the outlet of a runner to tail race. That pipe is called as draft tube. Okay, that pipe is called as draft tube. Now it is used, draft tube is used for discharging water from the exit of turbine to the tail race. ओके, मतलब जो भी एग्जिट है ड्राफ्ट ट्यूब का, वहां से जो भी डिस्चार्ज होगा, वाटर डिस्चार्ज होगा, दैट वाटर we are going to discharge to the tail race. That is the use of draft tube. Okay, and this pipe is that means this pipe of a gradually increasing area, that pipe is called as your draft tube. Okay, now one end of draft tube is connected to the outlet of runner. As I have explained, one end of draft tube is connected to the outlet of runner, while other end of that tube is submerged below the level of water in the tail race. um, the practical model of that for practical purpose also, we are going to use the same type. That means one end of that draft tube is connected to the outlet of runner, and while the other end of that draft tube is submerged below the level of water in the tail race. Okay, now in addition to serve a passage for water discharge, the purpose of this draft tube is another two purposes are there. First is, this draft tube permits a negative head to be established at outlet of runner and therefore increase the net head of turbine. Okay, that means by using the draft tube we can increase the net head of turbine. Okay, net head of turbine, so the turbine may be placed above the tail race without any loss of net head, and hence turbine can be properly inspected. Okay, this is the first purpose of this draft tube or use of this draft tube. And second one is, it converts a large proportion of kinetic energy which is rejected at the outlet of turbine, and these can be converted into a useful pressure energy. Okay, that means the draft tube is very much useful for converting a large proportion of kinetic energy which is rejected into a useful pressure energy. Okay, so draft tube is used to increase the net head of turbine. Okay, and so the turbine may develop more power, and also the turbine will be more efficient. Okay, that means efficiency of that turbine is also increased. Okay, now the types of draft tube. Here different types of draft tube I have listed. First is your conical draft tube, second is simple elbow tube, third is moody spreading tube, and last is elbow draft tube with conical inlet and rectangular outlet. Okay, now these are the different types of draft tube. I'll show the diagram so that you can easily understand. This is first, A is your conical draft tube. This is simple elbow tube. This is moody spreading tube. And this last one is draft tube with circular inlet and rectangular outlet. Okay, here you can see circular inlet and rectangular outlet is there. This is moody spreading tube, simple elbow. This is the shape of elbow, and this is a conical draft tube. Okay, the conical draft tube and moody spreading, this one, A and C, conical draft tube and moody spreading draft tubes are most efficient, while this simple elbow tube and elbow draft tube with circular and rectangular outlets, circular inlet and rectangular outlet, um, these require less space. Okay, the space which they require are less than the conical draft tube and moody spreading tube. Okay, and also the moody spreading tube and the conical draft tube are more efficient. Okay, are more efficient, and these two, simple elbow and draft tube with circular inlet and rectangular outlet, are they require less space. Okay, they require less space. Now these are the diagrams of types of draft tube, and this is the general introduction of the draft tube. How why the draft tube is provided and what is the meaning of draft tube. It is, you can see in the figure that the diameter of these tubes are gradually increasing. In every shape you can see that this is increasing area, increasing diameter here also. Okay, so move further for the draft tube theory. Here in this figure you can see that a draft tube is shown here. Draft tube is shown, that the upper side turbine casing is there. This is your inlet draft tube, inlet of draft tube, the tail race of whole plant, and this outlet of your draft tube. Okay, now here, why the figure y is there? So y is nothing but the distance of bottom of the draft tube from your tail race. Okay, so this is your height of tail race, you can see, say, at the bottom of your draft tube. Okay, and hs, here hs is the vertical height of draft tube above the tail race. Okay, this is your vertical height of the draft tube above the tail race. Now the two sections are there, section 1 and section 2. Here we are assuming both the sections, and at both the sections we are going to apply the Bernoulli's equation. Okay, Bernoulli's equation at this inlet and this outlet of the draft tube. Okay, so section 2 is at the datum. That means this line we are assuming as a datum, and this is your inlet of draft tube. Now by using Bernoulli's, I hope you remember the Bernoulli's equation. Here the pressure head is there. Here the v square upon 2g kinetic head is there. Hs plus y, as this is the inlet here, so height will be hs plus y. Second one, P2 by rho g plus V2 square by 2g, which is your kinetic head, at 0 plus HF. Okay, so as this is the outlet, here some of the losses will be there, and as it is a datum, so datum height will be 0. So HF is your loss of energy between sections, both the sections. As you have already aware about P2 upon rho g is your pressure head. Okay, pressure head plus this height. Okay, pressure head at this outlet and plus this height will be your P2 upon rho g. That means the pressure at the outlet. Okay, but atmospheric pressure is your Pa upon rho g plus height will be y. Okay, so substitute it in the above equation, you will get this one. Now here you can see that y will get cancelled, so second step is this, and sorry by simply um, substituting all these values, you will get the final equation of P1 upon rho g, that is the pressure P1 upon rho g will be Pa upon rho g minus Hs minus in bracket V1 square upon 2g minus V2 square upon 2g minus Hf. Okay, that means this equation proves that P1 upon rho g, that is this pressure head at the inlet of turbine, P1 upon rho g is less than your atmospheric pressure. Okay, is less than your atmospheric pressure. Okay, now this is about the draft tube theory. The second one is efficiency of draft tube. Okay, the efficiency of draft tube is defined as the ratio of actual conversion of kinetic head into pressure head in the draft tube to the kinetic head at inlet of the draft tube. Okay, that means efficiency kya hai? Efficiency of draft tube is the ratio of actual conversion of kinetic head into pressure head in draft tube to the kinetic head at inlet of draft tube. So mathematically we can write it as a eta d equals to actual conversion of kinetic head into pressure head at in the draft tube divided by kinetic head at the inlet of draft tube. Okay, now v1, as v1 is your velocity of water at inlet of draft tube. Before that, the theoretical conversion of kinetic head into pressure head in draft tube is, this is your theoretical conversion, v1 square upon 2g minus v2 square upon 2g. Okay, and the actual conversion of kinetic head into pressure head is v1 square upon 2g minus v2 square upon 2g minus hf. Okay, now here in this formula or relation, the v1 is nothing but your velocity of water at the inlet of draft tube. Okay, v2 is velocity of water at outlet of draft tube, and hf is the loss of head in the draft tube. Okay, this is your efficiency of draft tube. How efficient is particular draft tube we can find out by using this particular formula, that is the ratio of actual conversion of kinetic head into pressure head and the kinetic head at the inlet of draft tube. Okay, so we'll move further for second. That is the numerical of your draft tubes. Okay, the first numerical is a water turbine has a velocity of 6 meters per second at the entrance to the draft tube and a velocity of 1.2 meters per second at the exit for friction losses of 0.1 meter and tell water 5 meter below the entrance to the draft tube. Find the pressure head at the entrance. Okay, in this formula, sorry, in this problem numerical, they have given a draft tube at the turbine. Here the inlet of draft tube is shown, outlet of draft tube is shown, tail race is clearly shown, and they have mentioned that the water turbine has velocity of 6 meters at the entrance of draft tube. So at the entrance velocity will be 6 meters per second, so v1 is 6 meters per second, and the velocity of 1.2 meters at the exit. So V2 will be, that is velocity at outlet of draft tube will be 1.2 meters per second. Okay. Now again they have given the frictional losses of 0.1 meters. So HF will be 0.1 meters, and they have mentioned that tell water 5 meters below the entrance to the draft tube. Okay, 5 meters below the entrance to the draft tube, that means HS, that height HS is 5 meters. Okay, vertical height. Now we have to find out why they did not mention any value for y, and we have to find out the pressure head at the entrance, that means P1 upon rho g. Okay, same manner as we have applied for draft tube theory, here also we have to apply the Bernoulli's equation at the inlet and at the outlet of your draft tube. Okay, so here we are going to take this section 1 at the entrance and section 2 at the outlet of draft tube. Okay, so apply the Bernoulli's equation at both the ends. At 1 it will be P1 upon rho g plus V1 square upon 2g plus Z1, that will be equals to P2 upon rho g plus V2 square upon rho g plus Z2 plus HF, as this is the outlet of your turbine draft tube, sorry, we have to take the head losses HF. Okay, now here the Z2 value will be 0. Okay, HF they have given at 0.1, so we have to find out the remaining values. Now v1 by 2g we can find out, v2 by 2 rho g we can find out. Now the thing is v2 by 2g, sorry, printing mistake is there, v2 square by 2g. Now here z1 also we can find out by using 5 plus y, because this 5 value they have given and y we can simply write it as a. Now as we have done in the theoretical part for finding out P2 upon rho g, the P2 upon rho g can be written as your PA, that is atmospheric pressure head, PA upon rho g plus this Y. Okay, now this Y at the LHS and RHS will get cancelled. Okay, like this here. This Y and this Y will get cancelled, and by substituting all the values in the equation you will get P1 upon rho g plus 6.835 equals to PA upon rho g plus 0.1735. 4. Okay, now atmospheric pressure is also not given. As this is the atmospheric pressure, uh, if PA upon rho g is 10.3 meters of water, which is a general value, then we will get P1 upon rho g as the absolute pressure head at the inlet of draft tube. Okay, and if PA upon rho g, that is atmospheric pressure head, is taken as 0, then we will get P1 upon rho g as vacuum pressure head at the inlet of draft tube. Okay, if we take the P1 upon rho g, that is atmospheric pressure head, as 0, then the value, that is pressure head at inlet, will be vacuum pressure head. And if we take atmospheric pressure head as 10.3 meters of water, then the value of vacuum pressure head will be the absolute pressure head at inlet. Okay, now for that purpose only, we can take V1 upon rho g as 0, PA upon rho g as 0, and substitute it. You will get the value as P1 upon rho g equals to minus 6.6616 meters. As the sign is negative, it indicates the vacuum pressure head. Okay, vacuum pressure head. Now this is your first numerical. Now second one is on the same part. Second one is a conical draft tube having diameter at the top as 2 meters and pressure head at 7 meters of water discharges at the outlet with velocity of 1.2 meters per second at the rate of 25 meters cube per second. If atmospheric pressure head is 10.3 meters of water and losses between the inlet and outlet of the draft tube are negligible. Find the length of draft tube immersed in water. The total length of tube is 5 meters. Okay, 5 meters. In this numerical, they have given a conical draft tube. Diameter at the top, they have given as 2 meters. The pressure head uh, is given as 7 meters, and the velocity is also 1.2 at outlet. Okay, 1.2 as outlet, and the discharge is 25 meter cube per second. Atmospheric pressure head is given as 10.3 meters of water and the losses are negligible, so HF will be here 0. Okay, now as they have given that atmospheric pressure head is 10.3 meters of water, so here for the pressure head P1 upon rho g, we can find out the actual value of your pressure head by subtracting the 10.3 minus your pressure head. Okay, so 3.3 meters absolutely will be your pressure head at inlet. Okay, Now total length of the draft tube they have given as 5 meters. Okay. By using the discharge and area at inlet, we can find out the velocity at inlet. So V1 will be discharge upon area at inlet. At inlet, the diameter is 2 meters d1. Discharge they have given us 25 meter cube per second. So velocity at inlet is 7.957 meters per second. Okay. Now, uh, sorry. Hmm. Now, here by using same Bernoulli's equation at section 1 and section 2 we can find out P1 upon rho g as PA upon rho g minus HS minus V1 square by 2g plus V2 square by 2g minus HF. You have to by heart this formula simply you can find out. So here the HF is negligible, so HF will get cancel. Okay, P1 upon rho g we have find it out 3.3. Pressure head as atmospheric pressure head they have given us 10.3 minus HS we have to find out V1 V2 they have given. So this will be of simply we can solve it. So the simple mathematical calculation you can find out HS as 3.8464. Okay, so this is your HS. Hmm? Now the total length minus this HS will give you the height of your tail race. Okay, height of your tail race at the from the bottom of draft tube. So that height will be y equals to total length minus HS. Okay, minus HS will give you the height of tail race from the bottom of draft tube, that will be equals to 1.1536 meters. Okay, this is your all about the draft tube and efficiency of draft tube. Now we'll move further for the specific speed of the turbine. Okay, now what is mean by specific speed? It defines as the specific speed is defined as the speed of turbine which is identical in shape, geometrical dimensions, blade angles, gate openings, etc. with a actual turbine but of such a size that it will develop unit power when working under a unit head. Okay, this unit power and unit head, these are the unit quantities. Okay, so unit power means simply I'll explain it separately. Just for the introduction I'll explain unit power is nothing but the power developed by turbine working under a unit head. Okay, unit head means the height of 1 meter. Okay, so specific speed as I have defined, specific speed is nothing but the speed of turbine which is identical in shape, geometrical dimensions, blade angles, gate openings with actual turbine but of such size that it will develop unit power when working under a unit head. Okay, now this specific speed is denoted by the symbol of ns. Okay, symbol of ns. The specific speed is used in comparing the different types of turbine with, as every type of turbine has different specific speed. Okay, this specific speed is used in comparing the different types of turbines, as every type of turbine has different specific speed. Now, in MK's unit of power is taken as 1 horsepower and unit head is taken as 1 meters. Okay, as I have explained, unit head is nothing but the height of 1 meters. Okay, now the derivation of specific speed. For deriving the specific speed ns, first we have to take the formula for overall efficiency, that is eta O. Eta O overall efficiency can be find out by dividing or by taking a ratio of shaft power to water power. Okay, shaft power means the power which is developed. Okay, and water power we can find out by using rho g qh by 1000. Okay, rho g qh by 1000. So the power developed will be your p, and water power is rho g qh upon 1000. Okay, now here head is, h is nothing but your head. Okay, h is nothing but your uh, head under which turbine is working. Q is the discharge through turbine, and P is the power developed or the shaft power. Okay, so from this we can find out the power. P will be eta O into water power. Okay, so from this equation you can see that P will be directly proportional to Q into H. Okay, power is directly proportional to Q into H. Okay, so for Q we need D, which is diameter of actual turbine, N speed of actual turbine, U tangential velocity of the turbine, Ns that is your specific speed of turbine, and V is nothing but the absolute velocity of turbine. Okay, now these absolute velocity, tangential velocity and the head of turbine are related with each other. Okay, so the relation of these three is shown here, that is your u is directly proportional to v, that is tangential velocity is directly proportional to your absolute velocity, and the absolute velocity is directly proportional to root of h. Okay, root of h. So we can find out the tangential velocity. This relation of absolute velocity is by using flow ratio. Okay, now the tangential velocity we can find out by using pi d n upon 60. Okay, pi d n upon 60. So that tangential velocity can be again proportional to d into n. Okay, dn. Now by using these equations we can directly write down as root of h is directly proportional to dn, or d is directly proportional to root of h upon n. Okay, I hope you understood this. Very simple derivation is there. Now the discharge through turbine can be find out by using the AV continuity equation, that is area into velocity. So area will be B into D. Here area is calculated by using your width and depth, that is B into D. So B here is directly proportional to D. So can be write it as the area is directly proportional to D square. Okay, area is directly proportional to d square. And velocity, we have here written it as a velocity is directly proportional to root of h. Okay, so your discharge is directly proportional to d square into root of h. Okay, d square into root of h. Now by using this, we can simply adjust the values and write it as a h upon n square into root of h proportional to h raised to 3 by 2 divided by n square. Okay, substitute these values in the equation of power. You will get the power as k into h raised to 5 by 2 divided by n square. Here k is nothing but the constant of proportionality. We have vanished this proportionality sign. So as while explaining the definition, this is a unit power when working under a unit head. So power unit, as the power is unit power, we can write it as a P equals to 1, and as head is unit head, so head can be written as a 1. Okay, then specific speed n is ns. Substitute here, you will get P is 1, K is as it is, H raised to 5 by 2 is equals to 1 raised to 5 by 2, and N will be NS. Substitute and simply uh, do the mathematical calculations. You will get NS square equals to K. Okay, ns square equals to k. Now this value of k again substitute in the power equation. You will get power equals to ns square h raised to 5 by 2 divided by n square. Okay, so simply we have to find out the ns, which is specific speed. Make it at the one side of the symbol. You will get ns equals to n root of p divided by h raised to 5 by 4. Okay, n root of p divided by h raised to 5 by 4. This is the equation for your specific speed. Okay, this is the equation for your specific speed. Now we'll move further for the significance of specific speed. What is the significance of specific speed? This specific speed plays an important role for selecting the type of turbine. Okay, type of turbine. Now again we can predict the performance of turbine by using the specific speed. If we know the specific speed of turbine, we can predict the uh, performance of that particular turbine. Okay, so we move further for the numerical of this uh, numerical of specific speed. First numerical is turbine develops 7225 kilowatt power under a head of 25 meters at 135 rpm. Calculate the specific speed of turbine and state the type of turbine. Okay, before that, here you can see that for particular specific speed, the type of turbine is given. Okay, in MKS, 10 to 25 specific speed is there, then it is a Pelton wheel with single jet. 35 to 60 is there, then Pelton wheel with two or more jets. 60 to 300, then Francis, 300 to 1000, then Kaplan or propeller turbine. In SI, 8.5 to 30, Pelton with single jet, 30 to 51, Pelton with two or more jets, 51 to 225, it is Francis, 225 to 860, it is Kaplan or propeller turbine. Okay, these are the specific speeds and the type of turbine. Now, in this numerical, you can see that the power which is developed by turbine is given as 7225 kilowatts, and the head is given as 25 meters, and the speed is given as 135. Okay, so n is given 135, h is given 25, p is given 7225 kilowatts. Okay, we have to find out the ns value. Use the relation for specific speed. The relation is n root of p divided by h raised to 5 by 4. Substitute the n, p and h value, you will get the value of specific speed is 205.28 is the ns, that is specific speed. Now by using this value from the above table, you can see that as this is the SI system of units, this specific speed lies between 51 to 255. So the turbine is Francis turbine. Okay, so the turbine is Francis turbine as it ranges between 51 to 255. Okay, now the second numerical is a turbine is to operate under a head of 25 meters at 200 rpm. The discharge is 9 cubic. If the efficiency is 90%, determine specific speed of machine, power generated, and the type of turbine. Here specific speed of turbine we have to find out, power we have to find out, and the type of turbine we have to find out. They given the efficiency of turbine n, that is rpm, speed is given, and the head is given as 25. Also discharge they have given as 9 cumex. So by using the efficiency we can find out the power value. The overall efficiency is power divided by water power. So P divided by rho G Q H divided by 1000. By using this, we can find out the power. Power is comes out to be 1986.5 kilowatts. Okay, 1986.5 kilowatts is the power generated, and the specific speed by using this power we can find out by using the relation for ns. Ns is n root p divided by h raised to 5 by 4. Substitute all the values here, you will get the value of specific speed ns equals to 159.46 rpm. Okay, now the value of specific speed lies between the range of 51 to 255. Okay, so as it lies between 51 to 255, it is a Francis turbine. Okay, this is about the specific speed and the draft tube theory for turbines. In next video we will finish this chapter while studying the unit quantities and the specific curves, characteristic curves for the turbine. Okay, that will be the last part of the module. Up to this we have covered all the types of turbines and the design part of it, and also the draft tube theory and the specific speed. Okay, thank you.